Hi everyone, welcome back. This is Dr. Kofelt. I'm going to be ending our discussion of Chapter 3 of the Verge book tonight or today, depending on where you are, with the calculation of theoretical and percent yield of a reaction, and then following that with just a quick discussion of some types of reactions so that you can identify those. So we've determined how to do the limiting reactant, and we use the stoichiometry to calculate that. And so what we were actually calculating is what we call the theoretical yield. So in a perfect world, in a perfect environment, you would be able to get that amount of product if you had these two amounts of chemicals. So the theoretical yield is the amount of product that performs when all the limiting reactants react to form the desired product. It's the maximum that you can get, and it's predicted by the balanced chemical equation. That's why it's the theoretical version of this. But in the lab, what you're going to get is an actual yield. Okay, so that's the amount that you actually get when you do it in the real world and not in a perfect world, which does not exist. And so the percent yield tells us what percentage that actual yield that you found in the lab or in the real world is of the theoretical yield. So it's kind of like how good did you do. And so, if you get 80% yield, that's pretty good. Okay, that means 20%, you didn't. And so it's just the actual yield divided by the theoretical yield times 100, and that's your percent yield. So emergency oxygen supplies aboard aircraft are generated by the decomposition of sodium chlorate. And to determine the percent yield, if the decomposition of 75 grams of sodium chlorate generates 29.45 grams of oxygen, it is going to occur according to this balanced chemical equation. So for every 2 moles of sodium chlorate, you're going to produce 2 moles of sodium chloride and 3 moles of oxygen. Oxygen obviously is what you're wanting. Sodium chloride is a chemical that is inert. It's not going to harm anyone, and so that would be something that would be safe to do on an aircraft. All right, so the theoretical yield is what we're going to be able to get based on the balanced chemical equation. So we have 75 grams of that sodium chlorate, and it's a solid, so it's stable. Okay, again, a good thing on a plane. You don't want a bunch of liquids and gases on the plane if you can help it. All right, and so we need to find out what the yield is. Okay, so that's basically we're trying to see how much oxygen theoretically we could produce. So we need to see that 1 mole of NaClO3, and the formula weight of that is 106.35 grams. And again, I just added up all of those just like we learned how to do already. So that takes me from grams of sodium chlorate to moles of sodium chlorate. I'm producing oxygen, so I've got to do that mole ratio, right? Go to the top of the molehill. So for every 2 moles of sodium chlorate, it has to go on the bottom so it can cancel, I'm going to produce 3 moles of O2. Okay, and then I need to know how many grams that is, because I'm going to be comparing those grams in a minute to what the actual yield is. Remember, this is my theoretical. This is if it was perfect, in a perfect environment, this is what I would produce. And so it's O2, so there's 32 grams in 1 mole of O2. All right, now I want to bring this up while it's on my mind. you've got 106.35 and 2 moles on the bottom. Then when I tell you to do 75 times 3 times 32, enter, then you're going to divide, you're either going to divide by putting 106.35 times 2 in parentheses, or you can divide by 106.35 equals, and then divided by 2 equals. If you don't, what happens sometimes is you divide by the 106.35 and then you multiply by 2, and you're going to get your answer wrong. And so if you do it correctly in your calculator, you should get 33.9 grams of O2. And if you get 33.8 or something like that, that's okay, but you should get something really close to that, right? Not 2 times that or whatever, okay? Now it told us that the actual yield is 29.45, okay? So in order to figure out what the percent yield is, that's going to equal what we got, the actual 29.45 grams of O2, divided by the theoretical yield, which was 33.9 grams of O2, times 100. And so our yield was 86.9%. Okay? Not bad. So if you get 86.9, 90%, that's pretty good all day long. So that's how you do percent yield. Just don't forget this. Okay? That's what people tend to forget. But you gotta go over the molehill and do that moles to moles. All right? So in another calculation, you've got aspirin, which is acetylsalicylic acid, say that fast 10 times, is produced by the reaction of salicylic acid and acetic anhydride according to this reaction that I've got here, and I'm showing you the little bubbles. In a certain aspirin analysis, or synthesis, 104.8 grams of salicylic acid and 110.9 grams of acetic anhydride are combined. Calculate the percent yield of the reaction if 105 grams are produced. So what's actually produced is this 105.6. So you're not going to use that until the end. But notice, whenever you have two amounts that you start with, that should send whistles and bells off, okay? You're going to have to do a limiting reactant to see what the theoretical is, because your theoretical is going to be the lowest amount that you can make with those two chemicals. So we've got to do what we did before with our limiting reactant calculation. So we've got 104.8 grams of the salicylic acid, which is I'm calling sal, and this is the acetic anhydride. All right, and so I have 104.8 grams of the salicylic acid and 110.9 grams of the acetic anhydride, and it looks like the chemical equation is balanced, okay, and so everything is going to be on a 1-to-1 ratio, okay, so that's a good thing, right? So if it's balanced, then we should be good. All right, so 104.8 grams of salicylic acid and 110.9 grams of the acetic anhydride. All right, now you're going to have to get these numbers. So your salicylic acid is 138.13 grams per mole, and your acetic anhydride is 102.9 grams per mole. All right, so you got to have that. And then the aspirin, which is what you're producing, is 180.16 grams per mole. So that's what we're comparing everything to. All right, so 104.8 grams of salicylic acid times 1 mole of salicylic is 138.13 grams per mole, right? Times 1 mole of salicylic acid to 1 mole of aspirin times 180.1, what did I say? 6 grams of aspirin and 1 mole of aspirin. And that's going to give me 136.7 grams of aspirin. So then I do it the same thing for the acetic anhydride. 1 mole of acetic anhydride is 102.1 grams of acetic anhydride. And again, it's a 1-to-1 ratio. But that reminds me of how I get from the acetic anhydride to the aspirin times 180.16 grams of aspirin in 1 mole of aspirin. And that gives me 195.7 grams of aspirin, which would be great, except unfortunately I can only make that much because I'm limited by the amount of salicylic acid. So my theoretical yield is the one that's dictated by my limiting reactant. So I've actually produced 105.6. So when I want to do my percent yield, that's going to be what I actually got, which was 105.6 grams divided by my theoretical, which was 136.7 grams times 100. And when I calculate that, it's 77.2% yield. And this is one that we have done in the lab before, and if you get 77%, you're doing pretty good. It's a kind of a difficult synthesis to do, and it takes multiple lab periods, but anyway, 77.2% is what we got based on the theoretical yield due to the limiting reactant of salicylic acid. Okay, so and I do have some practice problems that you could do if you're in my class to further look at that. Okay, so the last thing we're going to talk about is just how to recognize certain types of chemical reactions, and there's just some simple types that we're going to look at now. We'll look in more depth at chemical reactions later, but these are just simple types of reactions. So if you have two things in your reactants and you make one thing in your product, you have combined two things to form into one, so that is called a combination reaction. If you start with one thing and you bust it apart into two or more things, you have decomposed it, so that's called a decomposition reaction. If you burn something, so you have to have oxygen, and your products are going to be CO2 and water, that is a combustion reaction. And you can always tell because you'll have those as your products, and you'll have a hydrocarbon added to oxygen. All right, and you notice that you produce liquid water and a gas of CO2. All right, so you just, again, apply those concepts that we just did. All right, you've got two things, then you're forming one thing, so we combine them. So that's combination. You have two things again, but one of them is oxygen, and our products are CO2 and water, so it is combustion. And sometimes you'll see this little delta symbol over here. That stands for heat. And then the last one, we've got one thing, and we split it apart into two things. And so that is a decomposition reaction. Simple, simple. Okay? All right. And that's it. We are done with chapter 3. Thanks for hanging with me if you've been here through all of them, or thanks for joining me for this topic if that's all that you were along for the ride. And I hope to see you again when I do chapter 4.